Hey folks, so today we're going to talk about a 4-bit ALU diagram using gates and all that. So first we're going to start with what ALU stands for, and it stands for Adaptable Long Underwear. No, I'm just messing with you. We don't actually really care about what it stands for. I don't really have any idea what it stands for. It's like Augmented Logic Unit or something stupid. But the reason why I make the underwear joke is because it kind of looks like upside down pants. So this is what a full ALU diagram looks like if you were to just draw it with like block diagram stuff in mind. But we don't really care about that. We want to go deeper than that and look at the gates because we're suicidal and we want to do that. So we're going to be primarily focused on the add function. So we're going to be adding two 4-bit numbers together, and just as a bit of review, this could be a 4-bit number. It's just any length 4 binary number. So if we want to add, say, 1000 with 0101, our ALU will take care of this. Now, specifically for this video, I just want to say right off the bat that I'm not going to be giving the absolute final gate level circuit, just because that the class I'm in right now, this is our first lab assignment. And I don't want to give out the answer because people don't learn that way. So the concept for those who are not in this class and are watching this because you like learning, this is the concept of the assignment. So you have two hex pads. So these hex pads go from 0 to F. So if you don't know what F is, I recommend you review some hex because we're going to be needing that for this exercise. Okay, so first, a little review of a full adder. Full adder. These are all arrows in case my drawings are kind of messed up. So when you have a full adder, if you're adding two 1-bit numbers together, you have a carry in, you have your sum out, you have a carry out, and then you have just your two numbers, A and B, going in. So if you want to add, say, 0 and 1, let's say A is 0, B is 1, and C in is 0, then you will have an S out of 1 and a carry out of 0. So that's just review. If you don't know what I'm talking about, I'd recommend you go over your full adders. So there's a few ways to do gate level full adders, and my favorite way is to do it like this. So we have an exclusive OR, which will be our S out, and we connect everything in there. This is going to be kind of messy, but this should just be review for most people. If you have a favorite way of doing full adders as well, then please do that instead. Just go with whatever you're most comfortable with. So here we're going to do A and B. Here we're going to do A and C in. The order of this doesn't matter. If you want to do A and B last, then whatever, it doesn't matter, because coming out from here we have an OR, and this will be our carry out. And then finally we have to do B and C. Okay, so this is what your full adder should look like, but I'm going to replace it with the block diagram I showed earlier, just for the sake of simplicity. Okay, so coming out of your hex pads, you have 4 outputs. And these are all binary numbers going from most significant bit here to least significant bit here. So if you input, say, 1000, which is just 8 on the hex pad, you'll have the number 8, and this is what's going to come out. So if you punch in 8 into your hex pad, this is your output. That's binary output. So if you have 0101, that is 5. So if you were to punch in 5 here, your output will be this. Okay? So for this assignment, and for just ALUs in general, we have to store input. So this is going to be our A number, and this will be our B number. So the way that you store output, or input rather, from a hex pad like this is to pop it into registers. And what are registers but just flip-flops? DQ. You know what? Screw this. Okay, so a register, in this case at least, is just a DQ flip-flop. So this is also known as the transparent flip-flop, where values don't actually change. So if you were to input 1, 1 will come out. And this is good for storage purposes, because when you plug in a clock, you can essentially control the lag of the flip-flop. So if you have a clock that beeps every second or so, that means that a value in here in your flip-flop gets stored for a length of 1 second. So that's very good news, because we want to store our input A. So you have your 4 outputs going into 4 DQ flip-flops forming a register. So that means they have 1, 2, 3, 4. You have a DQ flip-flop here, DQ flip-flop here, DQ flip-flop here, DQ flip-flop here, and you have outputs. These are not connected, so this is called a bunch of flip-flops in parallel, meaning that they're parallel to each other. They are not in sequence because they are not connected. They are separate from each other. Each flip-flop only deals with 1 binary bit at a time. Okay, so our register will have 4 outputs, which again, since it's a transparent, DQ is a transparent flip-flop, it's just going to be the same numbers, just that we have the capability to store them. So now we have to do our main addition function. With our full adders. And since we're adding 2 numbers, B, we don't actually have to store B in the assignment. So that means that this number will go here. And then here. Oh man, this is going to be super messy. I'm real sorry about this, guys. Okay, and then finally okay, so we're just adding both numbers together. So coming out of your register, you are just adding the numbers from the register with the numbers from your B hex pad. You're just adding them together. That's it. Okay, so now we have a cout coming out from our final full adder here. And guess what? We don't actually need it, because if we did use it, we'd end up with a 5-bit number. So if cout were 0, then you would have, I don't know, just for example, if your full adder ends up with the number 1, 1, 0, 0, if you had a carryout at the end, this would either be 0 or it would be 1. But since we're only dealing with a 4-bit ALU, we don't need that first number representing the carryout. So we just scrap that last carryout. We don't need it. And here we have our sums coming out. Okay, and also this is our carry-in, our original carry-in, and this is just 0. We don't have any carry-in to start with, so unless otherwise specified in the question, you won't need that carry-in at the start. So we have a bunch of sums coming out, and in this exercise we need another register to store the output. So let's call this the Y register, and let's call this the Z register. And again, these are just a bunch of DQ flip-flops in parallel. Okay, so now if you want to display the result of your addition, you will have your digital display. Boop, 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 boop. And this thing usually has 4 inputs as well. So then you just attach these. And that's essentially your ALU. There's a few other things in the assignment. So if you understand this and you're good just knowing this stuff, then you could probably stop the video here. But if not, then I'll show you some control switches as well. As we know, DQ flip-flops and flip-flops in general work with a clock. So this is our clock. Now, if you were to use a switch for your clock, I'm going to make an attempt at drawing a switch here. Oops, OneNote doesn't like me coloring stuff in. Okay, so that's a switch. If you wanted to use a switch for your clock, then you can actually make a control signal for the same flip-flop, turning it on and turning it off. Now in this class assignment, that's exactly what we have to do. So you would make a tri-state gate here, where your input would be from your clock switch. Your output will go here. So just a review of the tri-state, you have an input, you have an output, and then you have an on and off switch. So if this is on, then the signal, I'll change color for this, the signal will go all the way through. Okay? If it's off, then the signal's broken, nothing goes through, it's an undefined signal. So if you want to turn your DQ flip-flop off, you would have another switch that is honestly just an on and off switch. On, off. So this means that when the on and off switch is on, the clock switch signal will go through successfully, and your DQ flip-flop will register a signal and will keep the data that goes through it. It will store it. But if your switch is off, your on and off switch is off, then nothing passes through your tri-state, and the flip-flop is essentially just off. It won't work. So that's what a control signal is. That's what you can use for both your registers, actually. Now the final part of this assignment is a little bit convoluted. It wasn't explained too well. But my interpretation is if you have a XOR function on your ALU. So if you had your ALU pants diagram here, and you had two functions, you had add, and let's say you had XOR. So XOR, we can all agree that XOR is 1 if we have like 1, 0 going into a XOR. We can agree that this would be 1, but if this 0 suddenly became 1, our XOR would be 0. So that means that if the two numbers that are plugged into the ALU are the same, then we have a 0 exclusive OR output. If they're different, then we'll have a 1 exclusive OR output. So essentially what we're doing with the XOR function is asking our ALU, are the two numbers different? So I'm going to erase all this, and we'll talk about the XOR functionality. So you have two 4-bit numbers, let's say 1101 and 0001. The way that we can tell that these two numbers are different by splitting them up in bits. So we'll be dealing with this, we'll be dealing with this, we'll be dealing with this, and we'll be dealing with this. Now there's a couple ways to do this, but I think the most simple way would be to do something like this. So you have two numbers, A and B. So if A and B are the same, then you'll have an output of 1. Correct? So then if we have numbers C and D, so just for reference here, this is A, this is B, this is going to be, oops, what am I pressing here? There. Oops, what's going on? There we go. This is going to be C, this is going to be D. Okay, so I'm just kind of going down like that. So if you want to tell if these two numbers are the same, we can just do an AND here. Because if A and B are the same, this is going to output 1. If C and D are the same, this is going to output 1. If you have 1 and 1 in a regular AND, you're going to have 1. But since we have XOR, we only want one of, we want the numbers to be different. So if we put in a NAND, suddenly if this is 0, then our exclusive OR condition is not satisfied. So you can just repeat that for the other numbers here. You just add them all into your NAND. So you'd have a 4-input NAND with your output. And that's your XOR, pretty much. And the way that you would put that in your ALU is you just take your inputs from your hex, then through your registers, and you'd have a little LED light at the end, which will be on if your XOR condition is satisfied, denoting a 1, or off, oops, when your XOR is 0. So that's pretty much it. That shows you how to do an ALU with add and an ALU with XOR functions. Okay, so I hope that helped out. Thank you for watching. Feel free to subscribe, etc., etc. And apologies for the length, but I hope I went into enough detail. All right, see you guys later.